Hello, myself Professor Department of Electrical Engineering. I welcome you on a video lecture series of the subject Basic Electrical Engineering. So today we are discussing on single phase AC circuits. So today's topic of discussion in single phase AC circuit is AC through pure inductance. So before that, let us revise what is a phasor. A phasor is a vector which rotates in the anticlockwise direction about the origin with angular speed omega as shown in the figure. So here is the phasor whose length indicates the amplitude of the waveform, amplitude of the signal, and it's rotate in anticlockwise direction with an angle equal to omega t. Now the vertical component of the phasor V and I represent the sinusoidally varying quantities V and I. If we plot the projections of this vector of the phasor, then we will get the corresponding waveform. The complete rotation of this phasor in 360 degree corresponds to the one complete cycle of the sinusoidal waveform. So the one complete rotation corresponds to one complete cycle of this sinusoidal signal. The length of the line segment equal to the peak value Vm or the amplitude of the signal that either Vm or Im of an alternating voltage or current. Its angular velocity omega is equal to the angular frequency of the alternating voltage or current. The projection of phasor or any vertical axis gives the instantaneous values of the alternating voltage or current. The angle between the phasor and the axis of reference, that is 0 degree axis, it is a positive x-axis. This positive x-axis or 0 degree axis indicates the phase of an alternating voltage. So the phasor diagram, the diagram which represents the current and voltage phasors, and the phase relationship between voltage and current is called as the phasor diagram. Now let us see the AC through pure resistance. So if you apply a AC voltage source across a pure inductor, then what is the behavior of voltage and currents flowing through this inductor? To consider a circuit containing a pure inductor of inductance of value L connected across an alternating voltage source as shown in the figure. So here the alternating voltage source E is connected, where the E is or the V is alternating voltage is given by equation V is equal to Vm sin of omega t. So the alternating current flowing through the inductor induces a self-induced EMF or back EMF in the circuit, and which is given as V dash is equal to minus L di by dt. According to Lenz's law, it is the sign of this induced EMF is always taken as negative. So V dash is equal to minus L di by dt. So that much EMF will be induced in the inductor when we apply the alternating voltage. The quantity V is equal to Vm sin of omega t to a pure inductor circuit. Now, according to Kirchhoff's voltage law, the algebraic sum of potential difference in a closed circuit is always zero. So V is equal to summation of E is equal to always zero. That is V minus V dash is equal to zero. V minus V dash means what? Applied voltage is V. Vm sin of omega t plus this L voltage EMF across this L. The sum of that is always zero, means V plus V dash is equal to 0. But what is V? V is equal to Vm sin of omega t plus minus L di by dt, that equal to 0. So here you will get Vm sin of omega t minus L di by dt is equal to 0. So L di by dt is equal to Vm sin of omega t. Now di by dt is equal to, I have divided by L to both sides. Di by dt is equal to Vm upon L sin of omega t. Now, if we compare this, so since current I is a function of time, so the slope di by dt must be sinusoidally varying quantity. Hence, the current in the circuit is got by integrating equation 3 with respect to time. So let us integrate this equation. integrate this equation with respect to time t. So what we will get, integration of di by dt with respect to dt. Di by dt is integration of di by dt is equal to integration of Vm upon L sine of omega t. Okay, so but hence we will get I is equal to integration of di by dt is I, and that I is equal to Vm upon L is a constant. So Vm upon L into integration of sine of omega t is equal to L minus cos of omega t upon omega. So here you will get I is equal to Vm upon L into minus cos of omega t upon omega plus certain constant you will get. So since the current oscillates symmetrically about zero, the time independent component of current is also zero. So hence the integration of constant is zero. So I is equal to Vm upon omega L sine of omega t minus pi by t. Here minus cos of omega t, I have replaced it by law of trigonometry sine of omega t minus pi by t. So here I will get the equation I is equal to Vm upon omega L, it is nothing but Im. So I is equal to Im sine of omega t minus pi by 2. So here Vm upon omega L is nothing but IL, and current amplitude, it is nothing but the maximum value of the current. So the term omega L is here. Now what is omega L? It is analogous to the resistance and is called as the inductive reactance. This omega L term is analogous to resistance. And but as it is an inductive circuit, pure inductive circuit, this term is known as the inductive reactance, and it is denoted by letter XL. It is denoted by the letter XL. This XL is always equal to omega L, and omega is nothing but 2 pi FL, 2 pi L, 2 pi F. F here we indicate that F by mu. So XL is equal to 2 pi mu L. So it is the unit of ohm. Its unit is ohm. XL is nothing but your inductive reactance, and it is always XL is equal to omega L. Hence I can express this Im as Vm upon XL. Okay, we are see Im is equal to Vm upon XL. So you remember XL is nothing but your inductive reactance, and it is always equal to omega L, where omega is equal to 2 pi mu. So XL is equal to 2 pi mu L. So always you remember this thing. Now for AC circuit, XL and frequency, XL is directly proportional to frequency. XL is directly proportional to frequency. See here, the XL is directly proportional to frequency mu. XL is equal to pi mu L. So XL is directly proportional to frequency. Okay. So the frequency, if I increases, the value of inductive reactance increases. If frequency mu, if I decreases, value of inductive reactance decreases. Okay. So if I decrease the frequency to 0, so then it becomes a DC. If no frequency, then it is a DC signal. So for DC, mu, that is frequency, is always 0. Hence for DC circuit, XL is equal to always 0. Hence an ideal inductor offers no resistance to DC current. So remember why the ideal inductor offers no or zero resistance to DC, because your XL is equal to 0. And why XL is equal to 0? Because your frequency mu is equal to 0. That's why XL is equal to 0. And as XL is equal to 0, there will be no opposition to the flow. And that's why ideal inductor offers always zero resistance to the DC current. So from equation 1 and 4, what we got? We conclude that the current lags voltage by phase angle of pi by 2 or 1/4 of a cycle. So current is always lags the voltage by a phase angle of pi by 2. See here the waveforms of current and voltage. So this is the waveform for voltage, this is the waveform for dotted line, is the waveform for current, and your current is lagging behind. It lags by voltage by 90 degree or pi by 2 radians. So you remember this, and here is the corresponding phasor diagram. of the voltage. This voltage is V, okay, and it is making an angle of omega t at this particular instant of time, and here is the I, which is lagging behind by 90 degree. Okay, so you remember this. So also we can see that the current reaches its maximum value later than the voltage by 1/4 of the period t by 4 time. See, here my zero value of voltage waveform V appears first, then after t by 4 time my current value reaches to zero. Similarly, for maximum value, it reaches first, after t by 4 time current maximum value is reaches. So also t by 4 is equal to pi t2 upon omega. Now let us see the instantaneous power in a inductive circuit. So the instantaneous power supplied by or supplied to the inductor is equal to the product of the instantaneous current and instantaneous voltage, that we know that is P is always equal to V into I, that is instantaneous value of current into instantaneous value of voltage, that is nothing but your power. So the expression for the instantaneous power can be obtained by taking the product of instantaneous voltages and current. So instantaneous voltage is I and instantaneous current is, and instantaneous voltage is V and instantaneous current is I. So P is equal to VI, and it is nothing but Im sine of omega t minus pi by 2 into V is Vm sine of omega t. So while taking Vm Im is equal to sine of omega t minus pi by 2 into sine of pi by 2. So it is nothing but minus cos of omega t into sine of t. So minus Vm Im cos of omega t sine of omega t, and is equal to minus Vm Im upon 2 into 2 sine of omega t cos of t. Now we know what is 2 sine A sine B, 2 sine A sine cos B. It is nothing but sine of 2b. So it is sine of 2 omega. So it is Im minus Im Vm upon 2 into sine of 2 omega t. So the average power over one complete cycle of an alternating current is always P is equal to minus Vm Im upon 2 into sine of 2 omega t, is equal to minus Vm Im upon 2 into sine of 2 omega t. So since sine of 2 omega t is equal to 0, sine of 2 omega t over a cycle is always 0. Hence, what is the average power over one complete cycle? It obviously it is 0. So thus the average power supplied to an inductor over one complete cycle of AC is always 0. The average power always 0. So the pure inductance never consumes power. So we conclude that pure inductance never consumes power. So the average energy stored in an inductor is also can be given as energy stored E is equal to 1 half Li square joule. So you remember this. So this is for AC through pure inductor. So this is enough for today. So next time we'll discuss the AC through pure capacitance. Till then, goodbye and thank you.